So today we're doing section 3-4, which is real zeros of polynomials. Earlier this week we talked about what zeros were. Do you guys remember some of those other names for the zeros? Yep, an x-intercept, and what was the other one? Yep, what was the other one? The one I gave you.
The alpha.
The what? I thought you said the alphabet. It's a root, right? Okay, so a zero or a root. So if it's a real zero, that means it's not what type of zero? Imaginary, okay? Real zeros, because they are x-intercepts, can be found where? On the graph, right? On the x-axis of your graph. So when you're finding real zeros, you are going to use your graph to do that. We're going to find all of the rational and real zeros. So real zeros do include rational and irrational. And then I asked you to write the rational zeros theorem from page 253. So there's a blue box of information here. And we're just going to talk about what some of this means. So you have P of x equals, this says a sub n x to the nth, a sub n minus 1 x to the n minus 1 until you get to a sub 1x plus a sub 0. So I'm just going to go over what that means. If you have a sub n and x to the nth, the a is just representing the coefficient. Let's say n is 5, okay? If this was x to the 5th, a to the 5th would be its coefficient. When you do a to the n sub 1, what's 5 minus 1? 4. So they're just using the n minus 1 to say the previous term, the term before it. Okay, so this would be like x to the 5th, then x to the 4th. It would continue until you get down to x to the 1st, and then a sub 0 is the constant term. So this is just another way to show you a standard form of any polynomial. Okay? So it has integer coefficients. So integers are what kind of numbers? Whole numbers that are positive, negative, and 0. Okay? And then it says every rational zero of p is of this form, p over q, which is a fraction. So it is true, if it's rational, you can write it as a fraction. Even if it's a whole number, you could write it over 1. To find the possible rational zeros, what you're going to do is find p over q, and p has to be a factor of the constant coefficient, which the constant coefficient we usually just call what? We just call it the constant, right? It's just the number at the end of the polynomial if it's in standard form. And then the factors of the leading coefficient will be on the bottom. And then your factors of the leading coefficient, when your polynomial's in standard form, that should be the first thing that you see. So I said, how would you explain to a friend what that is? Okay, so hopefully somewhere in there you are doing p over q, where p is going to be the factors of the last number or the constant. Q is going to be the factors of the first number. And then once you get those factors, what do you have to do with p and q? Really, this fraction bar also means what? Divide. Okay, so you're going to divide to find what all of your possible rational zeros are. Okay, so you are going to use the rational zeros theorem to find the possible rational zeros. That is something that you did in Algebra 2, and something that we will revisit today. Okay, so if you need to take a second to write some of that in your own words, you can go ahead. And then we're going to look at example 1 and highlight what we have to do for example 1. All right, so for example 1, there are two things the directions are asking us to do. The first is to find the rational zeros. The second is to write the polynomial in factored form. Okay, so if you are writing the polynomial in factored form, let's just annotate what your factored form is going to be. Okay, so factored form means if your 0 is C, we talked about this yesterday, right? If your 0 is C, then the factor would be what? Good, x minus C. Okay, so you're going to have them in factors. Right? And then for the first one, we are going to find the rational zeros. And that's going to be our first step. So we're going to do this first, and then we're going to do this second. Okay, so you're going to be finding the zeros. Remember, the zeros are x-intercepts. So our first step is to list the possible rational zeros, and I just want to emphasize the word possible. Okay, it doesn't mean that these are actual zeros of the polynomial. It just means these are the possible rational zeros. So because we know that the zeros are x-intercepts, it makes sense that we are going to be graphing this eventually. But before we do that, we're going to use the rational zeros theorem. So we're going to use P over Q. So we just talked about what P and Q were going to be. Okay, so Logan, for P, those are going to be the factors of what number in my polynomial?
The coefficient of x to the third.
That'll be the Q. So on the top is going to be,
Of the constant.
yep, which is what for this?
75. Or
35.
35.
Yep, good. Okay, and then the Q is the factors of the leading coefficient, which is in front of x cubed, so that would be 1 if you don't see a number there. Okay, so it's nice when you have 1 that's on the bottom. So the factors of 35, I usually just list them in order. So 1 goes into 35 evenly, 5, 7, 35. Okay, remember factors means that the number divides into the value evenly with a remainder of 0. Okay, now what we have to do is divide these. Again, if you're dividing by 1, anything divided by 1 is just what? Itself. Okay, so we have 1, 5, 7, 35. For this, they are just going to be those top numbers. Okay, it's really when you have multiple numbers on the bottom where you're going to have to think about the division. So in step 2, we have to check which ones are actually zeros by using synthetic division. And you do need to use synthetic division for this, okay? Our goal is going to be to use synthetic division until we have a quadratic equation. Then you can solve the quadratic equation. And then to solve a quadratic equation, you can either factor, or if you can't factor, you use the quadratic formula. So that is why we want to get it down to a quadratic, because quadratics you can always solve using the quadratic formula, even if they aren't integers. So that is going to be our ultimate goal. Now it makes sense here that you can use your graphing calculator to check and see what they are. If you didn't, then you would just have to guess and check. So if I just picked a number out of these, let's say I just wanted to try to see if 1 was a 0. Okay, so I'm going to use synthetic division like what I did yesterday. So 1, negative 11, 23, 35. Okay, now Corbin, how would I know if 1 is a 0 of this polynomial? Right, the remainder will be 0, right? So I'm going to do synthetic division. 1 times 1 is 1. Add straight down to get negative 10. This would be 13. 13 times 1 is 13. Is my remainder going to be 0? Okay, so since r does not equal 0, 1 is not a factor. Okay, now I don't want to test all these. That's why it is beneficial to do what? Yeah, let's use the graph. All right, and then I am going to write a little note over here for you. So you can use your graphing calculator to find the zeros, which are the x-intercepts. But you must verify using synthetic division and you must solve a quadratic equation. Okay, so you don't have to use the quadratic formula, but at the very least you need to write out what your quadratic is and solve it. Now the reason why I want you to do this is because when we start off, we're only going to be finding the real zeros, but eventually we're going to find what type of zeros? Imaginary. And are imaginary zeros on the graph? No. Okay, so it's going to be helpful for us to use that process and continue to use that process when we go to imaginary, because it can be difficult when you get to some of the more complex problems. So when we graph this and look at our x-intercepts, you can look at them on the graph. Do you guys ever verify them another place?
The table?
Yeah, do you guys do that? So if you're verifying with the table, what are you looking for in your table? Yes, okay, so you're looking to see where the y is 0. Okay, so when I graph my equation, this is what I get. And this actually looks pretty nice because I can see where all of my x-intercepts are. It looks like the first one is where? At -1. This one looks like it's at 5. This one looks like it's 7. So you can pick any one of those that you want to test. Okay, so let's say I want to do -1. So I'm going to set up my synthetic division. And then again, I'll know if it is a 0 because what will I get at the end? I should get 0 as my remainder. Okay, so because 0 is my remainder, that means -1 is a 0 of p of x. Okay, and then we're going to practice finding the other ones using the quadratic. So I know this is a quadratic because if this is my remainder, this is my number term, this is my x term, this is my x squared. Okay, those are my coefficients. So the quadratic, I'm going to just label this, is x squared minus 12x plus 35. So I'm going to set that equal to 0 to solve. And then I'm just going to write the directions on the side. So set quadratic equal to 0 to solve. All right, this one looks like I can factor it. In fact, I know I can factor it. How do I know that? Really, the directions tell you that you're going to write it in factored form, and if you're going to write it in factored form, it has to be factorable. Make sense? So I have x and x. What's going to multiply to 35 but add to -12? -7, -5. Okay, so if I solve these, x minus 7 equals 0, x minus 5 equals 0, I would get x equals 7 and x equals 5. These are my other zeros. Okay, so all of the zeros that I found -1, I found 5, and I found 7. Okay, so now I'm going to write this in factored form. So I have to start with p of x equals, since that is my equation. P of x is what I was given right here. And then if we're doing this in factored form, remember we go from c to x minus c. So if I have -1, x minus -1 is, what's x minus -1? X plus 1, yeah? And then I would have x minus 5, and then x minus 7. Now, it doesn't matter what order those are in because they are being multiplied. Okay, so you just have to have those three factors. Okay, and then again, I just want to reiterate the reason why I'm having you do this process is to help us when we get to irrational zeros and imaginary zeros. Because I'm sure some of you are thinking, well, didn't we just find all the zeros here? Yeah, we did. How many zeros are there for a polynomial that looks like this? 3, because Logan, why? The degree, it's the degree, right? If the degree is 3, there are going to be 3 zeros. Okay, so then we'll do the first part of B together, but then I'm going to have you do the rest on your own and see how you do. So the first thing I want you to do is the possible rational zeros. Okay, so then Julian, on the top are going to be the factors of what number?
The last one.
Which is?
It's 6.
Yep, and it's -6, but really they'll be the same. And then Reese, on the bottom, I'm going to do the factors of what number?
-6.
Nope. So on the top is the factors of the constant.
Alright, so 3.
Yes, because 3 is what?
The leading coefficient.
Yeah, good. Okay, so for 6, I have ±1, ±2, ±3, ±6. For 3, I have ±1, ±3, and then I have to divide. Okay, so when I divide, if I divide everything by 1, I'm going to get those same things, right? So 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 1 is 3, 6 divided by 1 is 6. Now I have to divide everything by 3. So 1 over 3 is going to be ±1/3. 2 over 3 is ±2/3. What's 3 over 3? 1. Don't I already have that in my list? Yeah, so I'm not going to repeat it. And then 6 over 3 is 2, so I already have that on my list, so I'm not going to repeat it. So these are all of my possible zeros. And I want you to think about why this list is helpful, especially in a case like this.
If your graph goes off the side and you don't know it continues, now you can test all of them.
Okay, like if there was one outside of your window range. I was thinking in the first one, it's not particularly useful because all of those are whole numbers, right? And usually we can see when it crosses -1, 5, and 7. But let's say we have a graph that looks something like this, where it crossed, let's say this is 1, and this is -1. Okay, let's say it was something like this, okay? Now, this here, depending on your graph, might be hard to decipher, okay? Is that 2/3? Is it 1/2? Is it 3/4? But if you have a list that has all your possible rational zeros, then you can look at this and say, oh, 3/4 isn't a possibility, so I'm going to test 2/3. Does that make sense? Because 2/3 and 3/4 are pretty close together, 0.67 and 0.75. So that's where this list really is going to come in handy for us. Okay, so go ahead and graph it. And you can pick any of those zeros that you want to test. Right, so which one did you guys choose to test? 3? Okay. I will do that too then. All right, so if we test 3, because we can obviously see it's going through 3 here, that's great. Remember when you set up your synthetic division, you do want to watch out for what? Yeah, missing terms, because you need your placeholders. How did synthetic division go yesterday? You guys synthetic dividing at rapid speeds? Okay, so when I tested 3, I got 0 as my remainder, so that's awesome. Now I have a quadratic. Okay, so one of my rational zeros is going to be 3. Okay, 3 is a 0. I want you to understand that that's what this is verifying. Now that I have a quadratic, I have 3x squared plus 5x plus 2 equals 0. And then I'm going to go ahead and I'm going to solve that. So again, I'm writing this in factored form, so let's factor it. So what multiplies to 3x squared?
3x and 1x.
Yep, 3x and 1x. And then this is actually pretty nice because my only options are 1 and 2 and 2 and 1. Okay? So if I want to get 5, if I put 2 here, that's not good for business because 2 times 3 is 6 and I'm already over what I need to be. So you guys should be thinking about this, doing this yourself as well. Because if you're just copying it down from me but not connecting with it, it's really not going to make much sense. Right, so now we found our other 2 zeros. So I have negative 2/3 and negative 1. So I have negative 1, negative 2/3, and 3. Okay, I have 3 rational zeros. My degree is 3, so that makes me happy that I found all of them. And now I can write this in factored form. Remember from yesterday, I said that when you are writing these in factored form, you have to have what kind of coefficients?
Whole number.
Integers. Yep, okay, so you need integer coefficients. For factored form. And the reason why we're talking about this now is because you have a fraction, right? So we're not going to put x plus 2/3. Remember how we talked about that yesterday? If you put x plus 2/3, what you could do to make it all whole numbers? What can you multiply by? 3, the denominator. But for this, we don't even have to think about that. Don't I already have 2 of the factors here? Yeah, so I'm just going to put those to start. I'm going to have p of x equals, I have 3x plus 2 times x plus 1, and now I just have to write a factor for 3, which would be x minus 3. Okay, will you please double check yours to make sure that you put the p of x? Because I really don't want to take off points for you missing something that small. Okay, so your factored form of p of x is going to have p of x equals. Okay, and then you'll have it in factored form. Okay, questions for me on that part? Yeah, Reese.
So how did you get the 1/3 and 2/3?
Oh, for the possible ones?
Yeah.
So for the first row, I divided everything by 1, everything on the top by 1. For this row, I divided everything by 3. So when I did 1 divided by 3, I left it as 1/3. And then 2 divided by 3, I left it as 2/3. And the reason why I don't have 3/3 is because that reduces to 1. And then 6/3 reduces to 2. Okay? Good. Other questions for me? All right. Then we're getting into some other stuff. For example, 2. So you are going to find all of the real zeros. I said use the same steps in example 1. This first polynomial that I gave you is very special. So we're going to talk about all the different ways that you can solve it, but we're going to start by using the steps in example 1. Now I want you to notice that when it says find all of the real zeros, all of the real zeros include rational and irrational. And that's important because when you use the rational zeros theorem, you are not going to have the irrational zeros on there. Okay, so you're going to have to use your quadratic formula. All right, so the first way we're going to do this is just like we did in the first example. So this is going to be our first method. So method 1, we're going to do like we always do and do our P over Q. Okay, so Devira, factors of what go on the top?
For the top 4.
Yep, so that will be plus or minus what?
2, 4.
Good. Okay, and then Robert, on the bottom are going to be the factors of 1, which means when I divide them, what am I going to get, Robert? Yep, just tell me what they are.
1, 2, 4.
Okay, so plus or minus 1, plus or minus 2, plus or minus 4. Okay, so then when I graph this, I should see that some of these possible rational zeros are x-intercepts. Okay, so go ahead and do that. And then we're going to set up our synthetic division. All right, John M., what are my coefficients going to be for my synthetic division?
1,
Yep,
0,
yep,
-5,
mm-hmm,
0,
yep,
4.
4. Okay, so you started with x to the 4th. There's no x cubed, which is why you have the 0. X squared, there's no x, constant term. Okay, and then here you have your graph, right? So it looks like it crosses where? 2. Where else? 1, -1, -2. Okay, so we can pick any of those. What do you guys want to do? We'll do 1. So 1 times 1 is, you don't change, if you've already done it, don't worry about it. So 0 plus 1 is 1. 1 times 1 is 1. -4. Be -4. Be -4. Okay, so there we are. Okay, so this is a 0. Normally, in the other 2 examples that we've done, when we did this, we had a quadratic. This is not a quadratic, right?
No, it's not.
It is a what? It's a cubic, because this would be your number, x squared, x cubed. So aside from your remainder, how many numbers do you want here for a quadratic? 3. You want a, b, and c. So if that happens, you have to do synthetic division again. When you do it again, you have to use these as your coefficients, because what you're doing when you divide, think about it. If we're doing 1, that's like x minus 1, right, as your factor? So if you're dividing x to the 4th by x, doesn't it make sense you'd have x cubed? So if I have x cubed and divide that by an x, I get x squared. I'm trying to make it smaller so that I can get to a quadratic. So I'm just going to pick another number from our set. Well, you guys can help me. How about just 2? We'll do 2. Is that fine?
2 is cubic.
Say it again.
It's cubic 2. Like the result.
It shouldn't be if you use your new coefficients. So yeah, if you use the same ones, if you use the same original ones, it will be cubic because you're just dividing it by 1, which is why you have to use these. Okay, you can write out a new one. I just kind of hook them together. So 1 times 2 is 2. This would be 3, 6, 2, 4, 0. Okay, so now we have a quadratic. Yep, so that's why we have to use this one. So now that we have the quadratic, now we can set this up. I have, I'm going to put it here. I have x squared plus 3x plus 2 equals 0. And this one we said 1 was a 0, so here 2 is a 0. So now I'm going to factor. So I have x and x has to multiply to 2, add to 3, so plus 2 plus 1. So if I solve each of these, I'm going to get x equals negative 2 and x equals negative 1. So my total zeros are going to be 1, 2, negative 2, negative 1. So you can see I have 4 zeros. You can also write them as plus or minus 1, plus or minus 2. That's fine. I just wanted to show you that, yes, you do have 4 zeros total. Okay, now remember I said this one was special.
How do you know that it also has the opposite forms? Just by looking at it.
What do you mean by opposite forms?
The positive ones. Because right now you have negative 2 and negative 1 as your result. How do you also know that it's positive?
Oh, because once you test them with the synthetic division, you know they're a 0. So because your remainder was 0 here, 1 was a 0, and because your remainder was 0 here, 2 was a 0. So 1 and 2 from here, negative 1 and negative 2 from there. Yeah, that's how you're going to get all of them. Did any of you stumble upon another way that you could solve it? Were you guys thinking that there was another way you could do it? There's something special about the cubic function. Okay, so method 2, you could factor the cubic function. So this is x to the third plus x squared minus 4x minus 4. This is not going to happen all the time. This one is just special because it does factor. So if you're factoring your cubic function, you can factor by grouping. If you take out the x squared, you'd have x plus 1. Here you take out the negative 4, which is x plus 1. So you'd have x squared minus 1. Or sorry, minus 4. Times x plus 1. And then what does x minus 4 factor into? Yep, x plus 2, x minus 2, x plus 1 equals 0, which would give you the zeros, negative 2, 2, and negative 1. The 1 still comes from the synthetic division here. Now again, that's only going to work sometimes. And then what do you guys think the last way is? I thought some of you would try this right away. You can actually factor this. You can factor p of x, right? If you have x to the fourth minus 5x squared plus 4, that actually factors, right? X squared times x squared is x to the fourth. What's going to multiply to 4 but add to negative 5? Negative 1 and negative 4, which means this is going to factor to x plus 1 times x minus 1, x plus 2, x minus 2. So then from these, you would get negative 1 and 1, negative 2 and 2, and you'd have all 4 of them. So that would be like from the start. Okay. Again, that is rare, but I wanted to show you a unique example. And then we will go to part B. Right, so for part B, again, we are just going to use our first method where the first thing we want to do is pick out our possible zeros, so P over Q. You guys notice that the leading coefficient is 1, which means you're just going to have the factors of 4. So plus or minus 1, plus or minus 2, plus or minus 4. Those are going to be your possible zeros. Okay, and they are possible, not actual. Right, so then we're going to graph it in order to make some intelligent decisions. For how we're going to test these. And then I'm also going to see if you remember some things from your Algebra 2 days. And I don't have any missing coefficients here, so that's going to make my synthetic division setup quite nice. Be careful when you have two-digit numbers. Make sure that you give yourself enough space so you don't treat them as 1 and 0. Okay, so you can see your graph, so you can see where some of the zeros are. You can also see that the line is going to hit close to some zeros, but not exactly on them, because some of them are going to be irrational. So you can always use your table to check. See how I can see -1 on my table and 2 as my zeros? So those are going to be zeros that I'm going to test, okay? And again, it doesn't matter which one you do first. Should we do -1 first?
Yeah.
Sure. Why not? Okay, so then if I do 1 times -1, I get -1, which would be -5. And then when I multiply, I get 5, which would make this 4. 10 minus 4 is 6. -6, -4, +4. Okay, so remember your goal is to have a quadratic. Do I have a quadratic here? Nope. What do I have? What do I have? Yes, a quartic. Did you say a nice one? Okay, so this is a quartic, and then -1 is a 0. Okay, so we know that is going to be a 0. So for the quartic, I'm going to use my same setup here, and now I can try the 2 that I saw was a 0. So I'm going to bring down the 1. Yay, 2 is a 0 as well. What kind of equation do I have? Cubic. Okay, well, if it's a cubic, I don't see any more zeros here. Maybe I would try to factor it. Let me show you what happens. Okay, so if I try to factor it, I have x cubed minus 3x squared minus 2x plus 2. If I'm factoring by grouping, I can take out x squared, which would give me x minus 3, and -2, which would give me x minus 1. Do those match? Nope, so I can't factor it. Do any of you know what's happening?
It's going.
There's a
And how do you know it?
because it only touches the line. It doesn't like go through the line.
Yes, so in Algebra 2, you guys learned about multiplicities, right? Multiplicities. When you have a multiplicity that is even, so when I say even, I mean it's a multiplicity of 2 and not 3 or 5. It would have to be of 2, of 4, of 6. The multiplicity would have to. Then that means this 0 occurs more than once. Okay, so it touches it and comes back. It honestly looks kind of like a little parabola there. Okay, what it does is it just touches the x-axis, but it doesn't go through it. Okay, so this would be a multiplicity that's even. Do you guys remember what it looks like if it's an odd multiplicity? It looks like a cubic function. Yes, it bends through it. Okay, so it would look something like this. If you had it bend through the graph like that, then this would be an odd multiplicity, which means the 0 would happen 3 times or 5 times. Okay? So, where is that touchback happening? At -1, which means I'm going to use -1 again because it's the multiplicity. Now, if you forget about that, really, you could just test all the possible ones again, right? You could try all these, and you could see which one would give you a 0 remainder. -1 is a 0. That occurs twice. And then we'll write that the correct way when we write out our answer. I just wanted you to know that that is special. Right, so I'm going to write out my quadratic. So x squared minus 4x plus 2 equals 0. So I would try to factor this, x and x. Positive 2 is only going to be plus 2 plus 1, or minus 2 minus 1. Is that going to add up to -4? No, it's only going to add up to -3. So we can't factor, which means we have to do what? So we have to do the quadratic formula. Okay, and you should have your quadratic formula memorized. I'll write it down for you so you have it on your notes. Okay, so the opposite of b plus or minus the square root, b squared minus 4ac divided by 2a. So x equals the opposite of b, so 4, bless you. B squared is 16. I always do that part in my head just so I can deal with less evaluating later. And then minus 4ac, and then 2 times a, 2 times 1. Okay, so you have 4 plus or minus. 4 times 2 is 8. So this is 16 minus 8, which is going to give me square root of 8 here. Now, this is normally where people get points taken off because they don't know how to simplify with radicals. So the first thing you have to do is simplify the perfect squares, which would make this what? 2 root 2. Yeah, yep, you break it up into the square root of 4. Yep, times the square root of 2. And then the square root of 4 times the square root of 2 would give you 2 root 2. And if you guys need to make a side note that it's the square root of 4 times the square root of 2 would be 2 root 2. That's how we got from the 8 to 2 root 2. Now here's the other part that even some of us did wrong on our first test, right? You have to divide both of these by 2. You can't just divide 4 by 2 and then forget about this part. You have to divide both of them by 2. So this would be 2 plus or minus root 2. Okay, so these are your other zeros. So altogether, we're going to write out what our zeros are. So we'll start with -1. Well, actually, we'll start with 2. So we have 2, and then -1, we say with a multiplicity of 2 because it occurs twice. So -1 with a multiplicity of 2. And then here you can write these as plus or minus. That's fine. Just understand that those are 2 roots. So altogether, do I have the same as the degree? Yeah, my degree is 5. I have 1, 2, 3, 4, 5. Okay, questions for me on that one? All right, I'm going to let you practice these. So page 260. Okay, these are really important ones to practice. They are easy ones ones to miss, especially the ones where you have the square root in them. If you did not do as well on your last test as you wanted to, it is imperative that you are doing every problem. Okay, if you did well on your last test, you can do the ones that you need. Okay?